And let me move on to share screen as I usually do. Get that set up. Take me just a minute to do that. All right, let's enlarge here. More enlarging. Okay. Yeah, I'm going to review. Oh, let's see. My watch and my computer don't exactly agree. It's all right. Let me get the proper pen here. I'm going to review a little bit of what we did last time in the derivation of the path integral. We just made part of the way into it, and this part ends up with a fairly complicated formula. So let me try to go over it and hopefully help you see the forest instead of all the trees. So the propagator, yeah, question? Was there a question? Okay, so the propagator is basically the matrix elements of the time evolution operator. Here we're thinking about a one-dimensional problem with a kinetic plus potential Hamiltonian, and we'll make the thing in time independent. So the time evolution operator depends only on the elapsed time. So we take this u of t and we divide the time interval up into a large number of small intervals we call epsilon, where capital N is the number of intervals. So epsilon's t over n. And we factor this u of t into a product of n factors, each of which is a time evolution for a small time step. And then between these u of e factors, we insert resolutions of the identity x1 through xn minus 1. There's n factors, so there's n minus 1 slots in between the u's, and that's where these integrals are. And so that gives us a product of matrix elements of these u of e's, actually n of them running from the first one to the last one. By the way, the x0 is the initial. As you can see, it's the ket on the right side of this matrix element, and the x is the bra. It's interpreted as the final x, initial x on the right and final x on the left. In any case, the final x I'll also call x sub n, because that's how it works out with these subscripts x1 to xn and so on. Just another notation for it. In any case, we need to evaluate these propagators for a small amount of time, ultimately an infinitesimal amount of time, epsilon. So we take one of the factors that connects you from xj to xj plus 1 and write out the evolution operator in here, where t plus v means kinetic plus potential. The approximation here, which is valid when epsilon is small, is to replace this exponential of the sum with the corresponding products of exponentials, as if they were, as if t and v were commuting operators, which of course they're not. But the correction terms, which involve commutators, are of higher order in epsilon. So to lowest order, this is correct. And then what we do is we insert a resolution of the identity between the kinetic and potential energy terms, and that allows this matrix element to be evaluated, and it gives us this formula here. This is just to work it out, do the integral. So now to go back to the integral for the propagator, this is a product of n factors just like that. If you multiply them together, the prefactors get raised to the nth power, and the product of exponentials becomes the exponential of the sum, and results in this formula in the square box here, which is where we ended up last time. This is an expression for the propagator, and it can be regarded as a discretized version of the path integral. So I think that's all I did last time, and I still got about a minute left before the proper start time, so I'll stop now and not start with any new material. But are there any questions about this, where we ended up last time? This result is fairly complicated, so the first thing we need to do is to discuss it and make it more comprehensible. But as far as we got, are there any questions about that?
I guess maybe this is too long for how much time we have, but it doesn't really mess things up that we have a time evolution operator that only depends on the elapsed time. Like, is it too much trouble to do it with?
No, it's actually quite easy to do it. If the potential depended on time, it would be just as easy to do it, except these u of epsilons here would be u of you know, tn comma tn minus 1, and this would be tn minus 1 comma tn minus 2, and so on. And all of the rest of this could be carried through without any difficulty. I just made it a time independent Hamiltonian because it simplifies the algebra slightly, and the main idea is conveyed perfectly well by this approach. Actually, this approach is pretty easily generalized to higher dimensions, problems with time-dependent potentials. You can even add magnetic fields with a little extra trouble, but the basic idea is conveyed already in this 1D problem. That's why I did it that way. All right, any other questions about where we ended up last time with this somewhat complicated looking formula? All right, then let's get started on new stuff then. So let me take this page away. Well, let me bring it up anyway. Let me get this out of the way too. Clear some room on my desk here. Let me get this out of here. Let's do this. Yeah, so the first thing I want to talk about is how to comprehend this rather complicated expression. By the way, the limit n goes to infinity. We made an approximation here on replacing the product of exponentials, of non-commuting exponentials with the exponentials, replacing the exponential of the sum with the product of exponentials, arguing that that was valid to at least lowest order an epsilon. It's not exact, but the idea is that in taking the limit n goes to infinity, epsilon's going to go to 0. And so it's plausible, at least, that the answer we get when we take this limit is actually the exact answer, that the errors that are incurred here drop out when we take the limit. So that's the philosophy we're going to take here. Making this rigorous, by the way, is not at all a trivial matter. I wouldn't know how to do it by any means. All right, now then, so anyway, let's get some understanding of this formula. To begin with, let's look at these integrals dx1 through dxn minus 1. I think the way to understand them is by means of a space-time diagram. Let me bring that up, and I'll show you how that works. Let's talk about a space-time diagram. Let's remember that the propagator, the original propagator we started with, is parameterized, as you can see here, by the initial x, the final x, and the elapsed time. These three variables. Or if you like, we got a t0 here, but we set it equal to 0. It's really amounts to the same thing. So let me introduce a space-time diagram which clarifies, I think, those integrals. So on this diagram, I've got time running on the lower axis, and I've got x running on the vertical axis like this. There are two times, a t0 and a final time t, except t0 for us is equal to 0. And there are two x's, an initial x0 and a final x like this. And this defines a time interval and an x interval, which taken together give you a rectangle in the xt plane, which is, of course, is kind of a space-time diagram. The lower left-hand corner has the coordinates x0, t0, and the upper right-hand corner has the coordinates x and t, like that. Now then, we divided the time interval t from t0 equals 0 out to the final time t into a large number of small intervals, which I've indicated here, giving us times t1, t2, t3, and so on, all separated by the same time interval, delta t, which is the same thing as this quantity we called epsilon, which is a total time divided by n. That was the notation we were using. We inserted resolutions of the identity for each of the factors we had, n minus 1 of them, and they, in a sense, correspond to these n minus 1 intermediate times. Now, each of these resolutions of the identity was an integral over x. So there's an integral. So what you see is we get integrals over all the intermediate x's, but not integrals over the initial or final x's, which are parameters of the propagator. So as far as x1, for example, x1 is a variable that goes from minus infinity and plus to plus infinity. So let me indicate that by a dotted line here that runs down to this t1. And likewise, x2, let me indicate a dotted line running down here on the t2 line, x3, and so on, like so. And here's xn minus 2 right there, and here's xn minus 1, like this, dotted lines coming down. And so you can imagine that in this integral here, where you're integrating over all these intermediate x's that go from minus infinity to plus infinity, that x1 runs up and down this line between minus infinity and plus infinity, x2 this line, x3, and so on, like that. So you get range of integrations like this listed out one after the other for all the intermediate x's. All right. Now, if we go back to our integral and we imagine a certain point in this range of integration, that would mean a definite value of x1, x2 out to xn minus 1, all the intermediate x's. Let's imagine some point like that in this range of integration. So that means that x1 has some value. Let me put it here on its line. x2's got some value like that. x3's got a value there. Here's xn minus 1. Here's xn minus 2, or other way around, like this. We can put dots like that on these various lines. Now, next, allow me to connect these dots together, starting with the lowest line like that, going down like this. I forgot to put one in. Oh, I did. I put it in its way up there, like this. Let's say that after that it goes down. Likewise here, this goes down. It continues to go down here. Maybe it goes up after that. Dot, dot, dot. There's a bunch of ones in between. And you can see that by doing that, what I've created is a path which connects the initial space-time point in the lower left corner to the final space-time point in the upper right corner. And you can see that as each of these intermediate x's ranges between minus infinity and plus infinity, it's basically exploring all intermediate values of x that are possible in creating such a path, a discretized path going between these 2 points. Also, we want to imagine the limit as n goes to infinity. That's the limit we're going to take here, so that these delta t's get smaller and smaller, and therefore the number of points on the path grow to infinity. That's the limit that's involved in the integral. So you can see that what's happening here is that in a sense, these integrals over these intermediate points are turning into, and the limit when n goes to infinity, it's turning into a limit in which the variable of integration is really a path. There's a path space that emerges here. Let me call it script P. The path space is a set of paths x of tau. Let me call the time-like variable upon which x depends, let me call it tau, which has the properties that x of 0 is equal to t0, which for us is equal to 0 because I'm simplifying things. And then x of the final time, I'm sorry, not here, let me do it right. Sorry. We have a path space. It consists of paths x of tau, such that x of t0, which for us is the same thing as 0, is equal to x0, while x of t, which is the final time, is equal to the final x, which we're just simply calling x without any subscripts on it, like that. So let's think of that space of paths. And in a sense, what's happening in this limit is we're getting an integral over all the space of paths that have these fixed boundary conditions that are allowed to do anything in between. And so that leads to a change in notation, a more compact notation that looks like this. Let's take this integral dx1, dx2, dx1, dx2 out to dxn minus 1, xn minus 1. And let's replace it by a notation that looks like this, an integral over d of a path x of tau, where it's understood that the paths x of tau are taken over the path space P, which is indicated here. In fact, to simplify the notation even further, let me take that constant factor in front, which is mass m over 2 pi I epsilon h bar to the n over 2, and absorb that also. So let's make this notational replacement then on the earlier integral, and that takes care of this earlier stuff here and shows you an integration over path space. It's an infinite dimensional space of paths in the limit. Now, what about the exponent here? Let's take this exponent, which just came from doing Gaussian integrals. Allow me to factor out a factor of epsilon, which of course is the same as delta t. So I'll take an epsilon out of the sum. I have to turn that into an epsilon squared to compensate, and that epsilon I get rid of like that. And if you now think of epsilon as being a delta t, what you can see is that this sum has the appearance of a Riemann sum for an integral, Riemann sum approximation of an integral. You've got a delta x here between the two subsequent x's, xj plus 1 minus x of j, divided by twice delta t, epsilon's delta t, divided by twice delta t squared. So this is m over 2 delta x over delta t quantity squared, which is basically an m over 2 v squared. It's a kinetic energy, you see, it's looking like that, mass m over 2 v squared. And then here's a potential energy evaluated at the point v sub j. And so with those observations, the exponent looks like e to the I over h bar times something that in the limit looks like a Riemann integral. It looks like it's going to turn into this, the integral from 0 to t of d tau of m over 2 dx d tau quantity squared minus v of x of tau, that whole thing like that. That's what then appears in this exponent. And this, you may notice, is the same thing as the integral from 0 to t d tau of the classical Lagrangian evaluated at x of tau and x dot of tau. Because the classical Lagrangian for this problem is a function of x and x dot is equal to 1/2 m x dot squared minus v of x. And that's just what appeared after our magical Gaussian integrations. That's what we got up here in the exponent. So with those notational, oh, and by the way, the integral of the Lagrangian along a path x of tau is otherwise what we call the action functional, a of x of tau. The action functional, by definition, it's a functional of a path x of tau, and it's just given by the integral of the Lagrangian along the path. If we make all those notational changes, then our propagator, which is the matrix elements of the I'm sorry, again, let me do it right. The propagator, which is k of x, x0, and t, which is the matrix elements of the time evolution operator, can now be written this way: as an integral over the path space p of d of x of tau, and then we have e to the I over h bar, the action functional a of x of tau, like so. And let me box that because this is an alternative notation for the path integral, which we can regard as a compact notation, which in a sense is an abbreviation for this more explicit and much more complicated looking discretized representation. It has the same content here, looking like this. This compact notation has the advantage that it's easier to write down, and it's also easy to understand what it's really trying to say. You're integrating over an infinite dimensional space of paths. It's not all paths, they're constrained by the path space P, which has definite endpoints and end times. And as far as the integrand is concerned, it's a pure phase factor. It's e to the I over h bar times what is otherwise the classical action of the path, x of tau. Now, when we talk about classical actions of paths, it's basically integral of Lagrangian along the path. We don't necessarily assume that the path satisfies Newton's laws. In other words, it doesn't have to be a classical path. And that's indeed what we have here, because these paths, most of them are certainly not classical paths. Nevertheless, you can regard this as the action functional because it only involves classical quantities, classical Lagrangian, and so on. In fact, the only place that h bar appears in here is right there. You see, it serves as the unit of action to make the exponent dimensionless. All right, so this is the compact version of the path integral. Now, that's not done. We're not done with the understanding the paths that go into here, however. There's some more we need to think about. Let me go back to this diagram here that shows you a discretized path. And let's imagine taking, for some discretization, let's hold all of the intermediate x's, which are variables of integration. Let's hold them all fixed except for one of them. Maybe it's t2, x2 that we make variable. We hold all the others fixed. So this x2 then is going to run up and down its axis from minus infinity to plus infinity, but everything else is fixed. So the delta x that connects it with with x1 and the other delta x that connects it with x3, as x2 ranges up and down, both these delta x's are also going to go between minus infinity and plus infinity. And so what that suggests is that going into the path integral, if I can make a box for it, what it suggests is, oh, and by the way, that holds true no matter how finely we divide the time axis. As we let epsilon go to 0, it's still true that the delta x's go to plus and minus infinity. So what it suggests is that as delta t goes to 0, the delta x does not go to 0. And if that's true, it means the path x of tau is not continuous, because it means continuity means that the value of the function is the limit of the function. Here we wouldn't even have a limit, you see. All right. So if that's the case, then it means the nature of paths that enter into this path space, which I've written down here, consists of paths, all right, with fixed endpoints, but in between the paths are not even continuous. They're really crazy things. They can jump to an infinite amount or arbitrarily large amount of distance in an arbitrarily small time. Now, it turns out that's actually not the correct point of view to take with understanding the path integral. And the reason is that if these delta x's get to be too big, the oscillatory nature, these delta x's that appear, they are going to get large. And when it's being divided by the epsilon, which is going to 0, means that this thing is going to oscillate ever more and more rapidly. And when you take that into account, what you end up with is a realization that the delta x can't exceed too large a value. The epsilon here, of course, is delta t, in comparison to delta t, before the integral basically just oscillates itself to death. When I say an integral oscillates itself to death, what I mean is that it's rapidly oscillating integrand, and the positive lobe of one oscillation almost cancels the negative lobe of the next one. Typically, there's a parameter there that makes the wavelength shrink to 0, and as it does so, the cancellation becomes more and more perfect. And that's what happens here, is that delta x gets bigger and bigger, the cancellation gets more and more perfect. And if you take that into account, then what you find is that as delta t goes to 0, the range on delta x, which significantly contributes to the path integral, doesn't extend to infinity, but rather it extends to a distance, a distance which is of the order of the square root of delta t, like that. And so in that case, as delta t go to 0, delta x also goes to 0, and that means you see that the x of tau is continuous. So taking into account this fact about how the oscillatory nature of the integrand, we then decide, and this is just intuitively speaking here, but we come to the conclusion that this intuitive path, that this space of paths here should be regarded as containing all paths connecting the initial and final space-time points, paths which are continuous paths, not continuous paths. It's a better situation than before. But on the other hand, if we look at the velocity, delta x over delta t, the numerator goes like square root of delta t, and the denominator is delta t. So that goes like 1 over the square root of delta t. And therefore, that goes to infinity as delta t goes to 0. And so what we're seeing is that with this understanding on the range of delta x, the paths that enter into this path space are continuous everywhere, but they're differentiable nowhere. Essentially, they have infinite velocity everywhere. If you want to visualize what such a path looks like, mathematicians think about these kinds of functions all the time, differentiable everywhere, continuous everywhere, but differentiable nowhere. Weierstrass was the guy that started the study of such functions. But from a physics standpoint, if you just think about the trace on an oscilloscope for white noise, it gives you a pretty good idea of the kinds of paths that we're talking about. And those are the paths that enter into this path space like that. So that's contained then in this notation, d of x of tau integrated over this path space P. Now, if these paths are continuous everywhere but differentiable nowhere, then this calls into question our replacement of the exponent by a Riemann integral, because this is a Riemann sum approximation to a Riemann integral. At least it looks like it, but is it really? And the answer is no, it's not. It has to be reinterpreted as a different type of integral. It's called an Ito integral instead of a Riemann integral. That distinction won't concern us in this course, but I'm just mentioning it because these considerations do affect the exponent as well. In fact, for the applications in this course, it turns out that this exponent integral, which is basically an action integral, can be manipulated by the usual rules of calculus, as to say Riemann integrals, and you won't make any mistakes. But it's worthwhile mentioning at this point that there is this issue that appears there. All right, so with that understanding then about the nature of the path space, continuous but non-differentiable paths, and the meaning of the action and the exponent, this then becomes, this is the path integral for this one-dimensional problem that I've been talking about. And this one-dimensional example contains the basic idea, which carries through to multidimensional problems, problems with magnetic fields. It carries through to quantum field theory, where there are fields instead of particles, and so on. The same idea applies. So if you understand this, you've got a good handle on what path integrals are in general. All right. Now then, the K function on the left is the propagator, and it is oftentimes described in words by saying that it is the amplitude to find the particle at position x at time t, given that the particle was at position x0 at time t equals 0. And this language that we use for K follows from the fact, as I hope you'll recall, that the propagator is actually the solution of the time-dependent Schrodinger equation with a delta function initial condition, which is concentrated at time t equals 0 at position x0. If you just take that as an initial condition and solve the time-dependent Schrodinger equation, K of x, x0, and t is what you get. So that's a terminology, a reasonable terminology for the quantity in question. Repeat it. The amplitude to find the particle at x at time t, given that it was at position x0 at time t equals 0. Now, in quantum mechanics, amplitudes add, probability amplitudes add, and probabilities are obtained by the squares of amplitudes. And when you do the square of a sum of amplitudes, of course, they can interfere with one another, sometimes constructively and sometimes destructively. This is what gives interference patterns. It's one of the main essences of quantum mechanics. What we've got here for K is an amplitude, and in a sense, it's being represented as an infinite dimensional integral over other amplitudes. The integrand is an amplitude. And what does the amplitude represent? Well, in some sense, it represents the amplitude that the particle made it from its initial position, space-time position, to its final space-time position by following along the path x of tau. And what the integral is doing is summing over all those x's of taus. That's all it's doing. It's just adding up all the probability amplitudes of all the possibilities in which this process could carry out. There's a very beautiful picture which is described in a book by Feynman and Hibbs, and I want to tell you about it. I hesitate because I'm conscious of time, but it's such a pretty picture. Feynman and Hibbs talk about the standard double slit experiment. This is where you have a double slit hole like this. You have two holes like this, and you've got waves that come in here like this, and then you've got a screen over here, and you get an interference pattern. I think you know the general story on this. So the interference pattern is caused by the interference between waves which come out of these two holes like this, and when they reach the screen, they've got a certain phase relation, and they may either destructively or destructively interfere. I'm sure you're aware of that. So the phase on the screen then is a sum of two amplitudes that are added up and then squared. They're not squared first. They're added first and then squared to get the final result. Now, Feynman and Hibbs talk about, this is really Feynman's idea. Hibbs is the guy that wrote the book by taking notes in class, but it's Feynman's work. And the path integral, by the way, is generally credited to Feynman, although Dirac instituted some of the original ideas that led to it. But Feynman gets most of the credit for it. In any case, suppose we had three holes in the screen instead of just two. Well, then there'd be a third amplitude. And the amplitude seen in the screen would be a sum of three amplitudes like this. Suppose I put in a second screen like this. Then I have amplitudes for crossing through one hole and going there, crossing through one hole and going through the second hole, crossing this hole, going through that hole. You'd have all combinations of holes that you might go through. And the result on the screen at a point in the screen would be the sum of all these amplitudes, right? Now, what Feynman says is carry this further. Let's just slice up. Let's take this screen. Let's drill so many holes in it that the screen kind of disappears. Let's do the same thing with this screen here. In fact, let's imagine filling up the entire intermediate region between the source and the final screen, the detection screen on the right, with screens that have holes in them. And we gradually start drilling holes in them, and so that the screens actually get eaten up, and finally there's no holes left. Well, then what we're doing is we're adding up the amplitude to create the interference pattern on the final observation screen is a sum of paths that really are the same paths as in the path integral. That's what the path integral is. It's kind of like a double slit experiment in which the double slit screen has been multiplied an infinite number of times, and so many holes have been drilled that the screens actually disappear. And these are the amplitudes that one is adding up. So this is a picture, I think a very pretty picture that conveys some interesting ideas about the meaning of the path integral. And okay. The path integral constitutes a formulation of quantum mechanics which is independent of the usual one based on the Schrodinger equation. In fact, you can see it's based on Lagrangians, essentially because of the action here is the integral over the classical Lagrangian along the path. This is not a Lagrangian operator. There is no Lagrangian operator. It's a classical Lagrangian, but the paths are not classical. They're all these white noise looking paths. But still, this is based on the classical Lagrangian. All right, so those are some things about the paths.
Can I ask a quick question about the diffraction pattern metaphor?
Yes.
If you had an infinite number of holes infinitely close together, wouldn't it just act like free space? And so you wouldn't really get an interference pattern at the end? It would just look like a free particle, or?
Well, yeah, but maybe this wasn't plane waves. Maybe this was a point source, so it was radiating out, like that. And then you actually would have, I'm not drawing this very well. You actually would have the propagator with a point source, you see, as a delta function at a point source. Also, there's a question about whether you want it to be a time-dependent or time-independent problem, and I'm glossing over some of those details. But the basic idea I'm presenting is correct, is that there's a way of viewing the path integral as a dissolution of an infinite number of screens with an infinite number of holes in them.
Okay, thank you.
All right. Now then. So as I said, probabilities are squares of amplitudes. If you just had a double slit and you wanted to know what the probability was that the particle went through one slit or the other, by the way, you can measure that by looking to see which slit it came through. Of course, when you do that, you destroy the interference patterns, but you can do it and you can get probabilities. If you do that, then the probabilities are the squares of the amplitudes of passing through each of these slits, if there's only two of them. Likewise, in the path integral, we can ask ourselves, what are the relative probabilities of the various paths in this infinite dimensional path space that we take? Well, the answer ought to be the square of the amplitudes. But the amplitude is just a phase factor, as you can see. So when you square it, you get 1. And what that means is that all the paths that enter into this infinite dimensional space, they all have equal probability. All of them, including the crazy ones that run off to Mars in the first nanosecond and then come back in the next nanosecond. They have nothing to do with anything that looks like a classical path or anything. On the other hand, if h bar is small, we ought to get a classical limit, and we ought to expect something about having classical paths that connect the initial and space-time points that are contained in the propagator. That would be logical, wouldn't it? So how does this, and naively, you might expect that the classical paths would become more probable as h bar goes to 0. But that doesn't happen. All the paths are equally probable, independent of the value of h bar. So how does it happen? And the answer is this. It comes from the fact, as I mentioned earlier, that probabilities are the squares of the amplitudes, which are the sums of the constituent amplitudes. So if we have a path x of t in path space, in this very large path space, which is largely in phase with its neighbors in path space, then the phase factors that appear here constructively interfere with one another and make a contribution, a larger contribution to the result. On the other hand, if we have paths in path space which nearby neighbors are out of phase, that's to say the phase varies rapidly for small changes in the path, then they destructively interfere with one another and don't contribute. So this is a way of saying that the main contributions to this answer come from the regions of path space in which these phase factors are nearly in phase with one another. That would mean that if we had a path x of t, if x of t is a path in such a region of phase space, that means that it's approximately equal to a of x of t plus some small variation, delta x of t, like so. If these two are nearly equal to one another, then in some range around that path space indicated by delta x, they're in phase and we get a stronger contribution. Well, if we work this out to first order in delta t, the right-hand side of this condition is equivalent to saying that the functional derivative of the action as a function of x and t with respect to delta x of t is equal to 0. It's a way of saying that the action does not change to first order in variations about the path. And in terms of functional derivatives, an equation like this. Sometimes this is abbreviated just by writing that delta a of x and t is equal to 0. And this, as you may recognize, I hope you do, is the condition which is used in classical mechanics and Lagrangian mechanics. It's the condition that underlies the variational principle of Lagrangian mechanics, which is a powerful principle leading to the whole structure of the Euler-Lagrange equations, symmetries and invariants and everything that's done with that, and allows us to solve many problems in classical mechanics much more easily than they could possibly ever be done with Newton's laws. Hamilton's principle in classical mechanics was known 100 years before quantum mechanics. Hamilton, Jacobi, Maupertuis had some idea of it. Lagrange knew about it. They all knew about it in one form or another, and they used it very effectively for problems in classical mechanics. But why nature should endow classical mechanics with this structure, which causes the action to be stationary along the actual physically allowed orbits, that was something that was a mystery until the path integral came along something like 100 years later. I think this is one of the most remarkable theoretical accomplishments in physics, as an explanation of Hamilton's principle. All right, so the basic statement then is that the classical paths make their presence known not because they have higher probabilities on a path-by-path basis, but because they are in phase with their neighbors. And so it's the constructive interference amongst those neighboring paths which gives rise to the privileged nature of the classical paths. By the way, these phase factors, the fact that all the paths have equal probability, is true independent of the potential. The action integral involves the potential, all right, but the integral itself is just, it appears in a phase factor, so when you square it, you just get 1. What effect does a potential have? Well, it changes the interference patterns amongst paths and their neighbors. That's what it does, and that's how the classical paths makes its appearance. All right, now then, so this is the beginning then of the connection between the path integral and the variational formulation of classical mechanics. I'm going to say quite a bit more about it because it's most of what I'm going to be doing in the rest of this lecture, but that's at least the outline of it. I hope you remember enough of your classical mechanics course that you appreciate at least the general idea of this. All right, now, in order to explore this further, allow me to take the action functional of x of tau, and let me make a small variation about it called a delta x of tau. And let's evaluate this. Let's evaluate what happens when we vary the action about a given path x of tau. Initially, we don't have to assume that x of tau is a physical path, is a classical path. This can be any of these paths, including the crazy ones. However, both the paths x of tau and the path x of tau plus delta x of tau should belong to both of them should belong to the path space which I set up earlier. That's to say, they need to satisfy the endpoints, because that's what the action functional is defined on. The action functional is actually a mapping from that path space to the real numbers given by that integral. And so we need both these paths to be in the same path space. Well, if x satisfies the endpoint and end time conditions, it implies that delta x has to vanish at the endpoints and end time. So delta x of 0 is equal to 0 and delta x of t is equal to 0. This is just a conditions on the variation. So let's take this a of x of tau and delta tau. Let's write it out. So the Lagrangian is m over 2 x dot squared minus v of x, like so. So this is going to be the integral from 0 to 1 dt, excuse me, d tau. I'm using tau as t here is, I'm using t, here, let me do it right. Let me do it right. It's integral from 0 to t. T is the final time, so I'm using time as the final time of the path. So I need a different variable for the intermediate time, and I'll call it tau. So it's integral d tau, and then it's m over 2 x dot of tau quantity squared minus v of x of tau. Like so. That's what it is. This is what a of x of tau is. It's a definition of it. All right. Now, on the other hand, if I evaluate a on x of tau plus delta x of tau, this is integral 0 to t d tau, and then I've got m over 2, and then I've got x dot of tau plus delta x dot of tau, quantity squared, minus v evaluated at x of tau plus delta x of tau, like that, the whole thing, like so. That's the action evaluated along the neighboring path. Now allow me to expand this out in powers of the small parameter delta x. So the leading term is obtained by just ignoring the delta x completely, and you just get m over 2 x dot of tau squared minus v of x of tau, like that. The next order term, the first order term, is going to integral 0 to t d tau. And now you see we get the cross terms in the kinetic energy. There's a factor of 2, so it becomes m times x dot of tau times delta x dot of tau. And then for the potential expanding that out, we get v prime of x of tau times delta x of tau, like so. And the second order term is going to be 0 to t d tau. We can carry that in any order we want. We're going to have m over 2 delta x dot of tau squared. So that's the last term of squaring the kinetic energy. Then we get minus v double prime of x of tau times delta x of tau squared, like so. And you can keep on going to arbitrary order. Now let me call these three terms T0, T1, and T1 and T2. And there's higher order terms too. T just means term here. So just to identify them, like so. And let's take a look at them. So the T0 is the first term, and you can see it's just the unmodified action. That's just what you'd expect. The T0 is just equal to the action along the original path x of tau. That's all it is. As far as the T1 is concerned, let's take a look at it. We can do an integration by parts on the delta x of tau here and move the time derivative over to the x dot, which then becomes an x double dot. And if we do, we generate boundary terms. And so if I go to another page to just summarize what happens if you do that integration by parts, what we get is we get T1 is the integral from 0 to t d tau. And then we have minus m times x double dot of tau. And then we have minus v prime of x of tau. And then the whole thing is multiplied by delta x of tau, like so. And then there's the boundary term, which is going to be with an m, it's going to be x dot of tau, delta x of tau, evaluated between t and 0. Okay. But this boundary term vanishes because delta x vanishes at the endpoints. So it goes away. As far as T2 is concerned, let's look at that, the second order term. Here it is. Again, I can take this delta x of tau squared. Let me write it as delta x dot times delta x dot. Let's transfer one of the time derivatives over to the other side, and we need to change sign and do integration by parts. And if you do, what you get is this, is that T2 is the integral from 0 to t d tau. The first term is minus m over 2 times delta x double dot times delta x. And then we have minus 1/2 v double prime of x of tau times delta x squared, like so. And let me write this way in a different way, 0 to t d tau, delta x of tau on one side. The operator in the middle I'll write as m over 2 d squared d tau squared. And then minus v double prime over 2 x of tau. And then this x on delta x of tau on the other side, like this. So that T2 then, as you see, it looks sort of like a matrix element in quantum mechanics. There's an operator in the middle. There's a wave function on the two sides. And we do an integral to create the matrix element. It's not in the spatial integral, it's a time integral. But there's a similarity there. There's a definite, in the delta x here, the variation like plays a role of the wave function. We'll come back to the T2 later on. In any case, right now, let's concentrate on T1. Because what you may notice is if you look at, let me box it here. We'll put T2 on hold, we'll come back to it later. Let's look at T1. Let me bring it down here so we can look at it better. So this T1, one of the things you may notice is that the quantity in the square bracket vanishes if Newton's laws are satisfied, because that would be MA, this is minus MA. If this bracket vanishes, then MA, which is of course the mass times the acceleration, is minus V prime of X. Well, that's the force. So what we can say is that F equals MA implies that the term T1 vanishes. This means on the orbit X of tau. The second thing to say is that if T1 is equal to 0 for all choices of delta X of tau, let's say for all variations, looking back up here, here's the variation. If this integral vanishes for all variations delta X of tau, then the only way that can happen is the quantity in the square bracket vanishes. So that implies F equals MA. And thus we have the conclusion that the T1 vanishes if and only if Newton's laws are satisfied along the original path. When we did this expansion of A of X of tau plus a variation, we didn't need to assume that X of tau was a physical path, that is to say, satisfies classical equations of motion. But what we find is that if it does satisfy, what we find is that the first variation, the T1, vanishes if and only if it satisfies the classical equations of motion. So this is what's known in classical mechanics as Hamilton's principle. So let me just say something about Hamilton's principle then, is how it would be seen in classical mechanics. First of all, in classical mechanics, you would have an x0, t0, and let me draw it again in terms of a space-time diagram, t and x here. We've got an x0, t0, and an x and a t. And they, again, you can think of them as forming a rectangle here in the space-time diagram. And we have a space of paths, let's call x of t that join the two, x of tau that join the two. Let's call the space of paths P. It's x of tau, such that x of t0 is equal to x0, and x of t is equal to x, in the same notation as before. In fact, it looks like the same path that we had for the path integral, except in classical mechanics, we probably want the paths to be continuous because we're gonna differentiate them and things like that. Except for that, it's the same path space, I mean. The action functional then, A of x of tau, is in a mapping from this path space to the real numbers. And it creates the action by integrating the Lagrangian along the path. Then Hamilton's principle says, it says the following, is that x of tau is physical if and only, physical by means only one L, physical if and only if the first variation, delta A, with respect to x of tau equals 0. And this leads in a well-known way to the Euler-Lagrange equations in classical mechanics, that ddt of partial L with respect to x dot is equal to partial L with respect to x. So the Euler-Lagrange equations come out of this variational formulation. All right, now then. So this is a little bit of an elaboration then on the meaning of Hamilton's principle in classical mechanics, and which follows on our observation that these are in a sense the paths in the path integral. It's actually larger. You see, the space of paths for the path integral is a larger space of paths because they're not required to be differentiable. But what we find is that if they're in phase with their neighbors, then they are differentiable. In fact, they're classical paths. That's how the classical paths make their appearance. All right, now then. Here's an issue which arises, especially if you try to read the books. The books sometimes describe Hamilton's principle by saying it's the principle of least action. They say the action is minimized along the classical path. There's lots of books that say that. Maybe your own classical mechanics book said it. However, what you may notice from the variational formulation we just carried out is that all that we require to get the classical path is that T1 should vanish. And that's only the first functional derivative. Doesn't say, all it's saying is that the action is stationary with respect to variations in the path. First order variations in the path cause only second order variations in the action. That's not the same as saying that it's a maximum or a minimum. So I want to say something now about address the question about whether the action is a minimum or not. To do that, let me just talk about maxima and minima in general. So here's some elementary calculus now. Let's suppose I have a function f of x, and it goes up and down like this, and maybe it levels off and goes up like this. So we have a maximum there, and we have a minimum there. We have something there that's neither. And maybe another maximum up here. As you know, if you wanted to find the maximum or minimum of f of x, you'd look for roots of f prime of x is equal to 0. Let's call the root x bar. Let's say that x bar is a root. So x bar, here's an x bar, here's an x bar, here's an x bar, and so on in this diagram I just drew. Place where the derivative x0, x bar is called, in mathematics it's called a critical point. It just means that the first derivative vanishes. Now then, is this a maximum or a minimum? Well, you can see it can be any of them. It can be maximum here, minimum there, maximum there, and there it's not either one at all. This is not either one. But one way of telling which it is to look at the second derivative evaluated at the critical point. And the rules are this, is that if the second derivative is negative, then you have a maximum, because that means small deviations away from the critical point can only make you take on negative values, go downwards from the maximum. If the second derivative is positive, then you have a minimum. If the second derivative is equal to 0, like here, then it's inconclusive. You can't tell from the second derivative alone whether it's a maximum, minimum, or something else. So to go back to our action problem, if we ask, is the action actually a minimum along a classical path? The classical path is determined by finding a critical point in path space. That's the vanishing of T1. If you want to know whether it's maximum or minimum or not, you need to look at T2. We'll come back to that later. Let me say something about maximum and minimum in many dimensions. Let's take this x and just change the notation and make it x1. Again, I'm just doing pure math now, multivariable calculus. Let's say we got an f of x. We'll define a critical point f of x bar. We'll say x bar, let's do it this way. Let's say x bar, which is equal to x bar 1 through x bar n, is a critical point if the first derivatives of the function f with respect to x sub I evaluated at x bar are equal to 0, and this is for I equals 1 up to n. In other words, you could say you're at a critical point if the gradient of the function vanishes. Now, in many dimensions, what about maxima and minima? If I take let me do this. Let me write y is equal to x bar minus x, so that y is a deviation away from a critical point. If we take f of x and expand it about the critical point, it becomes f of x bar plus y times f prime of x bar plus 1/2 y squared times f double prime of x bar. Look at this. But the first term vanishes because that's the definition of a critical point. Let me make this let me carry this into a multidimensional notation. F of x is equal to f of x bar. The second term would become 1/2 the sum on I and j of yi, yj times the second derivative of f with respect to xi and xj evaluated at x bar. So if you want to know whether this is a maximum, a minimum, or something else, you need to look at the second derivative, which is a matrix. It's an n by n matrix now. And in particular, you need to look at the eigenvalues of this matrix. Let's call these lambda i's here, lambda i's, these eigenvalues. So here are the cases. If all the lambda i's are greater than 0, then this means the second derivative term is a positive definite form in y. And it means that you're actually at a minimum because small changes can only raise the value of f. If all the lambda I are less than 0, then you're at an absolute maximum. If some lambda I are greater than 0 and others are less than 0, then you have a saddle point. That means that as you move away from the critical point in some directions, it goes up, whereas in other directions, it goes down. And finally, if some of the lambda I are equal to 0, if some 0 eigenvalues, then the result is inconclusive based on the second derivative, the second derivatives only. All right, so this is some multivariable calculus. All right, so that's how it works for the critical points. Now, to go back to our question about whether the action in a mechanical problem is really a maximum, a minimum, or something else in actual Hamiltonian mechanics, we obviously need to look at T2. T2, you can see, is a quadratic form in the variation delta x. In fact, let me call this operator here in the middle B, just to give it a name. B doesn't stand for anything. I just called it B. If I do this, then this T2 can be written in kind of a Dirac notation this way, as delta x, B delta x. So this is now in a function space, and so B is an operator in infinite dimensions. It can be thought of as a linear operator. You can see it's a linear operator here at x on functions delta x of t. So if B is a positive definite operator, meaning that all of its eigenvalues are positive, then it means we're actually at an absolute minimum, because the small variations can only raise the action away from its minimum value. If this were a negative definite operator, all the eigenvalues were negative, then we'd be at an actual maximum of the action. If we had some eigenvalues were positive and some were negative, we'd have a saddle point in the path space. Okay. Now, none of this matters for classical mechanics. You don't care really whether it's maximum, minimum, or something else, because it's the vanishing of the first term is what gives you the equations of motion, and that's usually what you're interested in. But in the case of the path integral, the relation between the path integral and the classical orbits, the T2 does matter. It affects the phase of the propagator, as it turns out. That's why I'm going into this. All right, in any case, this is how you can answer the questions about maximum, minimum, and so on. Actually, an obvious question at this point is, since all the books say the action is maximum, and we now realize that's not necessarily true, the obvious question is the action really maximum, or when is it maximum, if ever? So the answer is this. It is that in a kinetic plus potential problem, the action really is a minimum. They call it least action. The action really is a minimum if the time is short enough. But as time goes on, if you make the time longer and longer, gradually what happens is some of the eigenvalues of that B operator turn negative. And so you end up getting a saddle point in function space. That's what happens in typical mechanical problems. All right. Now, next, I want to tell you about the stationary phase approximation. Stationary phase approximation has to deal with integrals with rapidly varying exponents. The type of integral I want to look at, let me call the integral I just stands for integral, is let's say variable x, and it looks like this. It's e to the I of phase factor phi of x, which depends on x, but I'm going to divide it by a parameter kappa, which we want to think of as going to 0, being small. We'd like to understand the behavior of such an integral, especially as a function of kappa. In practical applications to the path integral, kappa is going to be replaced by h bar, and we're going to think of h bar as being small. But let me just do some of the math first of the stationary phase approximation. Here's the basic idea, is that if kappa gets small, then what happens is that this phase factor oscillates more and more rapidly. It's just a phase factor, so its magnitude is plus and minus 1, but the wavelength can be changed as a function of x. In any case, what you get is you get oscillations that go like this, up and down. And as kappa gets smaller and smaller, these oscillations get thicker and thicker and shorter and shorter wavelength in the interval. And as they do, the integral of a positive lobe, in a variable of integration, more and more closely cancels out the integral of the neighboring negative lobe. And the result of that is that as kappa goes to 0, the value of the integral also goes to 0. Now, on the other hand, this picture that I've drawn here with canceling neighboring lobes works best when phi of x has a non-zero derivative. In other words, phi prime of x is non-zero, because it means that a small change in x corresponds to a small change in first order change in phi. On the other hand, if you're at a place, let's call it x bar, where phi prime of x is equal to 0, that's to say at a critical point of the phase function phi, then what you find is that there's one lobe which is larger than the others and is not canceled by its neighbors. And so the result is that this integral, when kappa is small, is dominated by regions of the variable x near the critical points of the phase function phi at phi of x. So let's do this. Let's let x bar be a critical point of phi of x so that phi prime of x bar is equal to 0. Let's let y is equal to x minus x bar. Let's take phi of x and let's expand it in powers of y. So we get phi of x bar at lowest order. We get y times phi prime of x bar. We get 1/2 y squared times phi double prime of x bar. I kind of presented the same expansion a few minutes ago. The middle term vanishes because by definition of a critical point, that's 0. So this integral I then is approximate. Now it's an approximation. Is it can be approximated by writing integral dx of e to the I over kappa multiplied times phi of x bar plus 1/2 y squared, do it right, y squared phi double prime of x bar plus higher order terms, which I'll neglect. All right. Now the first is just a constant phase factor. You see, it can be taken out of the integral. And what's left over is a Gaussian integral in y. Well, the dx is equal to dy because it's just a linear change of variable you see right here. X bar is a constant. So it just becomes a Gaussian integral in y, which is doable. So this then gives us an approximation to this integral, which looks like this. It becomes the square root of 2 pi kappa times I divided by phi double prime of x bar times e to the I over kappa times phi evaluated at x bar. And so the idea now is this, is that this integral was dominated by regions of x space near the critical points, because near the critical points, phi didn't change very much, i.e. it was in phase with its neighbors when x changed only by a small amount around x bar. And by taking advantage of that fact, we get this approximation. You can see part of the approximation involves the phase factor where phi is evaluated at the critical point. And the rest of this square root stuff, is giving you, in a sense, is giving you an indication or a quantification of how rapidly phi dephases as x moves away from x bar. All right. Now phi double prime, I'm assuming here, is not equal to 0 at x bar. I'm assuming that. It may or may not be true, but I'm assuming that. You'll recall that's what's needed to tell whether you really have a maximum or a minimum. If phi double prime were equal to 0, we'd have to carry this expansion out of cubic order, and I don't want to do that because that's not part of this course. But if you're motivated, you can do that. All right. Assuming phi double prime is not 0, it might be either positive or negative. And so we have the square root of either I or minus I. And so let me rewrite this in a different form. I'm going to write it as e to the I nu pi over 4, which is a phase factor coming from the square root of I, times the square root of 2 pi kappa divided by the absolute value of phi double prime of x bar, multiply times the phase factor e to the I over kappa of phi of x bar, like so. All right, so this then is what's called the stationary phase approximation for the original integral. All right. Now I'm not quite done with it because critical points in general, they're generally not just one of them. If we go back to our even one-dimensional problem here, here's a problem that has 1, 2, 3, 4 critical points. Let's index these critical points by a branch index I'll call B, a discrete index. And if there's more than one critical point for this function phi, then the value of the integral is just given by a sum over those critical points. So I'll put a sum on branches B like that. If I do, then I have a x bar has a branch on it here and it goes in there. By the way, I never defined what nu is. Nu is just the sign of phi double prime evaluated at x bar. So if x bar is a function of the branch, then so is nu. That just gives you whether you're taking the square root of plus I or minus I under the square root here. In any case, let me box this part off because this is the 1D. This is the 1D stationary phase approximation. All right. Now, if I do a multidimensional stationary phase approximation, if I go back to the same formula up here, but I reinterpret x as a multidimensional variable and phi is multidimensional, and you go through now the multidimensional algebra, you now have a multidimensional Gaussian, an n by n Gaussian matrix, and the y now becomes this quadratic form. And so you need to find the eigenvalues of the phi double prime matrix in order to get the phases right. But in any case, when you do all of that, what you're going to end up with is a formula that looks very similar to this. The nu here is going to be replaced by the difference between the number of positive and negative eigenvalues of the second derivative matrix. But except for that, it's a sum over the critical points, and it looks very similar to this one-dimensional problem. Now let's go back to the path integral. In the case of the path integral, to write it out, we have the integral d of x of tau. And then we have e to the I over h bar, the action function. This is not a, this is k. The action function of x of tau. Now, based on what we've said, this is dominated by the critical points of the variable of integration, which is the critical points of the exponent. But those, in fact, those in fact are the classical paths. Yes. Yes, question?
No, sorry, I was just going to ask if you can move the paper. Now it's good.
Yeah, sorry, it slipped. But the critical, let me call the critical paths x bar of tau. What are they? They're the roots of variation of the action evaluated at x bar of tau is equal to 0. That's solving the classical equations of motion. So these are the classical paths. So let's take x of tau and write it as x bar of tau, the classical path, plus let's call it y of tau. Y of tau just really means delta x means the same thing. So y is the deviation away. And let's expand this exponent. Then we get k is the integral d of, I'll put this Phyllis in a minute, e to the I over h bar, a evaluated at x bar of tau. The first order term vanishes. And then the second order term is going to be second order variation in the action. But you see, that's the same thing as this y sandwiched around that b operator. Like that. That's what it looks like. And as far as d of x of tau, x bar is a constant path, so d of x is the same as d of y, and I can put y of tau here if I want. This first phase factor involves the classical path, which is independent of y. So it can be taken out of the integral. Then what's left is, as you can see, it's a Gaussian integral. It's a huge Gaussian integral, an infinite number of dimensions. It's a Gaussian integral in the variations about the classical path. And so the way to do it is to diagonalize the b operator. You find its eigenvalues and eigenfunctions, you diagonalize it. And once you can do that, then you can do all the Gaussian integrals and you get a whole bunch of phase factors. All right. So I'm going to skip most of the details of that because I think they're too technical for the course. But I wanted to give you the general idea of what's going on here so that you understand the general features of the formula that finally emerges. Before I address that final formula, let me just address a simpler aspect of this problem, which is simply the phase factor that you get on evaluating A on the classical path. That is, I say, something that comes out of the integral. This involves A evaluated on the classical path x bar of tau. Now, A is a functional, it's defined on the infinite dimensional path space, but x bar is a specific path in that path space, one that satisfies Newton's laws. So this A for a specific path, this is just a number, is all it is. But it's a number that depends on the parameters of the path space, which were the x, x0, and t for our problem. And so this quantity A of x bar of tau depends on the parameters of the path space. And so it's in effect becomes an ordinary function of these three parameters. I'll give us a different symbol for it. I'll call it S of x, x0, and t. This function is given a name. It's called Hamilton's principal function. Hamilton asked himself the question, once you have, he probably thought it was a minimum action. Once you minimize the action, once you made the action stationary, and you get the equations of motion, is there something special about the value of the action along those stationary paths? And that's what led him to look at this function S. And it turns out there's special properties of this function S. Here's they satisfy some differential relations. Here's what they are, discovered by Hamilton. One of them is, let me go back to my path space like this. Here's the x0 and time 0, and here's the final time x and t. And we've got now a classical path satisfying Newton's laws, x bar of t, that connects the two together. What Hamilton discovered is that if you take the derivative of s with respect to x, the final x, you get the final momentum. That's to say, it gives you the momentum p of the path at the final time. If you take the derivative with respect to the initial s, x0, you get the negative of the initial momentum, the p0 down here at this point. And if you take s with respect to the time t, you get minus the Hamiltonian, that's to say minus the energy at either time, because we're using a time-independent problem here. So these are called generating function relations, and were discovered by Hamilton. I'm just mentioning that as interesting properties of this function S, which is otherwise the action evaluated in the classical path. In any case, when you do all the work of that infinite dimensional Gaussian integral, what you find then is an expression for the propagator that looks like this. There's a phase factor that I'll write as e to the minus I mu times pi over 2. It's a multiple of pi over 2. It's divided by the square root of 2 pi I h bar. This is still for a one-dimensional problem, kinetic plus potential. We then have the absolute value of the second derivative of Hamilton's principal function with respect to the initial and final x's to the 1/2 power. And then we have e to the I over h bar times Hamilton's principal function s of x, x0, and t. And so again, the idea here is that this is the classical, this phase factor, that's the integrand of the path integral evaluated along the classical path. And the rest of this is giving you information about how rapidly the paths dephase as you move away from the classical path. And so what range or what region of path space are in phase with one another and contributing to the final amplitude. The mu that appears here is an integer, and it's related to the number of negative eigenvalues of that B operator that I spoke of before. In fact, that's what it is that mu is equal to the number of negative eigenvalues of the B operator, which is needed to get the phases. The operator of the B operator, which involves the second variation in the action. All right. Now I'm almost done with this except for one more thing, and that is that given our path space, with our initial xx0 and final xt, in general, there is more than one classical path that connects the two. A lot of books make a mistake about that, and they talk about the unique path connecting the initial and final points, but that's wrong. The paths are in general not unique. If you don't believe me, look at a particle in a box. It's easy to see there's multiple paths, and it's discussed in the notes. But this is like finding you see multiple critical points of even a one-dimensional function, as I illustrated earlier in the graph. Normally you have this. So we need to sum over those. I'll call them branches. The branches then are the classical paths connecting initial and final space-time points. This means that the action function depends on the branch, and so does the mu here. The mu here is, by the way, it's called a Maslov index. Never mind where that came from. Russian mathematician discovered it. Actually, our people argue about that. Some people think Joe Keller at Stanford discovered it first. In any case, this gives us a formula which is sometimes called the Van Vleck formula. This is giving Van Vleck more credit than he deserves because he didn't get all the details of this. But anyway, it amounts to a semi-classical approximation to the propagator. And it's interesting not only for the fact that it's a useful approximation in many circumstances, but also it establishes yet another connection between quantum mechanics and classical mechanics. Okay, now, although this is rather intimidating looking formula, in some cases it's not hard to use. Let me talk about the free particle. Let's do the free particle. If I go back to my same space-time diagram of t and x here, with initial and final x0, t0, and x1 and t1, x0, t0, x1 and t1, or x, let me make t0 equal to 0, and final x and t like this. Then the classical path is a straight line for a free particle. We know that. It's a straight line, and moreover, the velocity v is equal to the final x minus the initial x divided by the time. This is the x bar of t. That is to say, it's the classical path. It satisfies Newton's laws. So you know what it is. The Lagrangian is, of course, 1/2 mv squared. It's just the kinetic energy because there's no potential. But v is constant along the path. So the integral of L d tau from 0 to t along the classical path is just equal to Lagrangian 1/2 mv squared times the elapsed time t. That's all it is. By the way, let me make a slight digression, because what I should have done is I should have cited the free particle for the free particle, the propagator for the free particle, which we worked out exactly using quantum mechanics earlier. And this was in the last lecture, I think. The formula is this: it's the mass divided by 2 pi I h bar times the time t to the 1/2 power times e to the I over h bar, the mass times x minus x0 squared divided by twice the time. And you may wonder how I remember this formula. This is the free particle propagator, exact. We did it by quantum mechanics. One of the ways I remember it is that the exponent here is actually the classical action. This is coming up here. You see, it's the integral of 1/2 mv squared t, but v is x minus x0 over t. And if I plug this in here, like that, this turns into the m over 2, x minus x0 quantity squared divided by the time, which is precisely the exponent that appeared here from the quantum calculation. Now then, so this means that Hamilton's principal function then, which is a function of x, x0, and t, for the case of the free particle, is m times x minus x0 squared divided by 2t. And is my pen running out of ink? It is. Fortunately, I have another one. I have a trash can, throw the old one away. All right, so this is Hamilton's principal function. So now we get an opportunity to test Hamilton's relations. Let's compute partial of s with respect to the final position x. What does that give us? Well, differentiating here, you see the 2's cancel and you get m times x minus x0 divided by t. But x minus x0 over t is the velocity, that's m times v, and that indeed is the momentum at the final endpoint of the free particle orbit. What about ds dx0? That should give us minus the initial momentum. Well, now there's an extra minus sign from the chain rule. It becomes minus m times x minus x0 divided by t, which is equal to minus mv. And indeed, that is minus the initial momentum because momentum is conserved. So it works. Finally, what about the energy? partial of S with respect to t should be the Hamiltonian, or the energy, or with a minus sign. Taking the derivative with respect to time, the time appears in the denominator. I now get m times x minus x0 squared over 2t squared with a minus sign. And you see that's minus m over 2v squared, which is the kinetic energy, which is minus the Hamiltonian. And so that works as well. So these are the generating function relations that Hamilton worked out in general, exemplified by the free particle. If we then take the second derivative of f and use the Van Vleck formula up here, you'll find the Maslov index is 0 because the B operator is positive definite. You will get this prefactor exactly out. It's a version of the second derivative here. You'll get it exactly. So this is all then as a way of saying that in the case of the free particle, the Van Vleck formula and this big Gaussian integral that we did in function space gives us the exact propagator. This again applies to Hamiltonians, which are quadratic functions of the Q's and the P's, and so it'll also work out for the harmonic oscillator as well. All right, that is all I want to say about path integrals. In fact, I feel like I said too much because it takes a long time to say it all. There's more in the notes than I've lectured on. Some of the stuff that's in the notes I think is kind of too technical for this course, and I'm not going to ask you to read it. So in particular, I'm not going to ask you to go through the detailed derivation of the Van Vleck formula. You don't need to know about that, but it is worthwhile having a general idea of what it means and where it came from, and that's I would like you to understand that. So when I hand out the homework and stuff, I'll indicate by the reading assignment which parts of the notes you should read and the ones that you can skip. Of course, you can read the parts I say to skip. You can read them anyway if you're curious, if you want to learn more about this. All right, so that's then all I want to say about path integrals. Are there any questions about this? If I could summarize what I've done, I've defined the path integral, introduced the infinite dimensional function space, which is the main concept that lies behind the machinery of it. Then the main effort on working with it was to develop the semi-classical approximation to it. In addition, there are things you can do with the path integral that don't involve semi-classical approximations. They're useful for a number of problems. And I'll give at least one of those in the homework, and you can think about some of that. In addition, you'll see in the notes, again, this is a section I'll ask you to skip, but you can use it also for statistical mechanics. There's a brief introduction to that topic as well. So anyway, with that, are there any questions about the path integral? All right, well, if not, then I'm going to take the next few minutes to make a beginning on the next topic for the course, which is charged particles and magnetic fields. Maybe I just have time to remind you of the setup. We've talked about the Hamiltonian for charged particles and magnetic fields before. If it's the electric field as well, then the Hamiltonian is this. It's the kinetic energy is 1/2mp minus q over c, the vector potential A, which is allowed to depend on both x and t, squared plus the q times the scalar potential I call capital phi, which is a function of x and t. In general, it's a function of both space and time. So this is the Hamiltonian for a particle of charge q and a given electromagnetic field, at least ignoring spin and other effects that we will consider later. Now then, also remind you about gauge transformations. Under a gauge transformation, if the new gauge is indicated by primes, and a prime is equal to a plus the gradient of f, where f is what I call the gauge scalar. It's a function of x and t. The scalar potential phi prime is equal to the old one, minus 1/c df dt. And as I explained in an earlier lecture, the wave function also has to change. That psi prime of x and t is equal to a phase factor, which is e to the I q over h bar c times the gauge scalar f of x and t multiplying the old wave function psi of x and t. In other words, the new and old wave functions differ by a space, in general, a space and time dependent phase factor. So these are some of the basics of this Hamiltonian. Based on this Hamiltonian, it's reasonable to define what I'll call V, a velocity operator. We're doing quantum mechanics, so observables are operators. A velocity operator, if I just copied the classical formula, would be 1/m times p minus q over ca. But if you want a quantum justification for this formula, one way to do it is to say that this can be obtained from the Heisenberg equations of motion. That's to say it's x dot according to Heisenberg. It's 1/IH bar times the commutator of x with h. And you had a homework problem in this, so I don't think I need to go over that, repeat that. But let me just remark that if you take this we will take this as a definition of the velocity operator for problems involving particles in magnetic fields. And if we use this definition, we can plug that back into the Hamiltonian and then rewrite the Hamiltonian in the following form. It becomes m/2v squared plus q phi of x and t. And what this shows you is that the Hamiltonian, even for including magnetic fields, even time-dependent electromagnetic fields, the Hamiltonian is still the sum of the kinetic plus the potential energy. It's just that the kinetic energy is written in this rather complicated way. In fact, that's the physical meaning of this rather complicated term, is that it's just the kinetic energy. All right. So that's the barest introduction. And in the next lecture, we will consider the problems of charged particles in magnetic fields, starting with the case of the uniform magnetic field. It's otherwise known as the Landau problem. It's an important problem in condensed matter physics and also in astrophysics. And so that's what we'll do on Thursday. Are there any questions about this very brief introduction to problem particles in magnetic fields? I think this is mostly review what I've done here. Any further questions?
Is the velocity operator does correspond to an observable, right?
Yes, it corresponds to observing the velocity.
Okay.
Any other questions? All right, if not, then I shall stop the screen sharing. And I shall stop the recording.